Alright, so we've received this SECDEC code word. And we don't know. It could have errors, it could not have errors. We have to determine that. And so the first thing I always like to do, obviously this is when you're doing it on paper. If you were to be making a circuit doing this, it would be different. You wouldn't have to necessarily label the bits. But that's what I do, is I label the bits first. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And let's underline our check bits. 2, 4, 8, and technically this is also check bit, I guess, but it's our dead bit, right? It's our super substantial, important one. I guess it's no more important than the rest of the bits. I don't keep saying that, but it's just a little different. So what do we need to do here? Well, we need to first kind of just go through the same process for our sec code word, in that we need to look at our data bits and calculate what the sec bit should be. And I might be getting ahead of myself. Let's write our code word, or let's write our check bits that we received over here. So we're going to say 8 is a 1, 1, 2 is a 1, and 1 is a 1. And eventually we're going to get our calculated bits as well. We don't include our dead bit. Our dead bit is just going to kind of chill there. We'll look at it later. So let's start calculating what our check bit should be. So we'll do it purple, and we'll do C1. Oops, and that equals the XOR. Wow, that's a bad looking R. That's better. Okay, of 3, 5, 7, 9, and 11. So 3, 5, 7, 9, and 11. We got 4 1s. That's an even number already, so our parity bit can stay as a 0. C2, C2 is a function of 3, 6, 7, 10, and 11. So 3, 6, 7, 10, 11. And so that means it needs to be 1, right? There's 3 1s there. And now we'll do C4. Oh man, I can't make R's to save my life. There we go. So we got C4 is the exclusive OR of 5, 6, 7, and 12. So 1, 1, 1, 0. And so this parity bit comes out to be a 1. And C8. And what do we got here? Well, it's 9, 10, 11, and 12. So that is 1, 0, 0, 0. And what's this come out to be? Well, it comes out to be a 1. All right. So let's put this in, right? We've got our calculated check bits, and remember, make sure we do them in the right order, right? 8, 4, 2, 1. So 1, 1, 1, 0. Now let's XOR these, right? So we're doing the XOR function, and what do we get? Well, we get 1 and a 1, that's a 0. 1 and a 1, that's a 0. 1 and a 1, that's a 0. 1 and a 0, that is a 1. So our syndrome equals 0, 0, 0, 1. So our first thought is like, oh, bit 1 is corrupt. But now hold up. we need to check and see if there are two errors, and our dual error detection bit can help us do that. So what we need to do is, we know that our dual error, let's put down here, we'll do a little dead column. So for our dead bit, for our received, we've got a 1. Now let's calculate what our dead bit should be. And now here's where people commonly make mistakes. They say, oh, these are what our check bits should be, and these are what our data bits are. So I'm going to use these check bits and these data bits. False. Do not do that. When we're calculating, right, C0, or our dead bit, we need to XOR only the received bits. All of these calculations should always only be done on the received bits. So in this case, we should be calculating the parity bits on these values here. So XOR of, well, let's do it now, 0, 0, 0, 1, and how many ones do I got? Whatever. 1, 1, 1, 1, 1, 1, 1, 1. Jeez Louise. All right, in this case, I screwed that up. I'm going to count the ones here. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9 ones. So what does that mean about our even parity? Well, it should be a 1 to make it a total of 10 ones, which is even. So our calculated dead bit is a 1. And so ask yourself, if there was a single error, this parity bit should be wrong, right? They shouldn't be the same. But here, the received is the same as the calculated. And so what that means is, if our dead bits are the same, if our received and calculated dead bits are the same, and our syndrome is not all zeros, that means there are two errors. So let me write that. We'll say Rx dead equals, so they don't have to be 1. Just, if they equal our calc dead and our syndrome does not equal all zeros, then we have a single error. We have two errors, right? Then we have two errors. Don't know why that E is capitalized. You might just have to get over it. So we've got two errors there. That's what is happening in this specific example. There are two errors, and don't say, oh, but wait, maybe this is one of the bits that's wrong, and if I put this in, and then don't fall in that trap, because it won't work. It doesn't work like that. All we know is that there are two errors. In this case, all we can do is the receiver can say, hey, there are two errors. I can't correct it. Will you repeat that data? So this is SECDEC in action.